Alright guys, after a glass of water, I feel just revitalized, and we can just dive into the recitation problems again. So I'll be covering the section 4, which is probably missed by all the 9 a.m. session students. My apology for that once again. But you actually didn't miss out on much, because this section, all the four, well, there are 4 questions in total, but the first 3 questions are really kind of, how do I put it, weird questions. They're atypical in the sense that you'll probably not see them during exams or during homework, but you will definitely see them when you're actually working with real-world data set. So although this section is titled Decision Tree and Beyond, but it's actually, once we go into the details, you'll see that this actually concerns something that's way bigger and way more generalized than just decision tree model. Okay, so hopefully that you will learn something useful from these weird atypical questions. Okay, so for question 4.1, once again, please excuse the screen size for the data table here, because everyone should have their recitation notes ready on their computer, so I won't bother actually just blow this window up. So hopefully you are following me here. This is pretty much like the typical data table that you will see with the decision tree problem. We have 4 features, which I will denote as capitalized axis. Sorry, this is actually uncapitalized 1. Okay, and 1 target variable y. Okay, and you're given the data set here. The training data set contains 6 data points. So the natural question that we want to ask is, okay, now our task is once again trying to build a decision tree on this training data set. How do we build that? Well, there's only one way that we know, learning from this class, that is using ID3 algorithm. And using ID3 algorithm meaning that we're going to have to fix on a criterion for splitting node, or for finding the first node to split, and that criterion will be mutual information, which I denote as simply MI. Okay, and to be more exact, this will be mutual information of target Y on a particular feature X. Okay, so let's see, you have the data, and you can actually work it out, the details. And I won't waste your time because I won't actually have to wait for you to finish it. This is a pre-recorded video, so I can just give you the answer right away. If you were to follow this criterion down to the letter, then the first node that you will find will be X4. Why? Let's try to calculate its mutual information. By definition, the mutual information of Y and X4 will be the entropy for Y minus the conditional entropy of Y given X4. And this term here is really a weighted sum of X4 taking on any particular value, the probability of this thing, times the conditional entropy of Y given that particular value. Okay, following me? And if you go back to the data table, then you can see right away that this thing is the same for all the different values from 1 to 6. This is going to be 1/6. What's more important is that once you fix the value for X4, and then you go back to the data table, then there's only one Y. There's only one Y data point associated with any of the values for X4 here. Okay, so if you have only one Y, then what's the entropy? Well, that's easy. The entropy of a random variable that takes on only one value is, of course, just 0, right? And this is true for any I from 1 all the way to 6. Okay, so if that's the case, then this whole thing will just go away to the 0, and we will arrive at the mutual information for y between y and x4 to be simply the entropy of y itself. And we will prove later that this is actually the maximum mutual information between y and any variables that you can get. Okay, so of course this will be the biggest number, and of course the ID3 algorithm and the mutual information criterion will tell us these two things. Will actually tell us, oh, go ahead, choose x4. This is so useful. Okay, so let's just follow it and grow our tree. X4 is at the root. We split on its value. And arrive at the tree that looks like, let me try to be correct here, minus, plus, plus, minus, plus, minus. Okay, so let's try to find the next attribute to split out. But wait a second. You can see that there's no need to split the tree any further. We're done, right? Because every leaf node here at the end of the tree is containing just one single example of y. One single sample point, one single target variables, and there's no point in splitting just one sample into, I don't know, subsamples, right? So we're done with the algorithm. This is our tree. That's it. Life is over. Oh, sorry. I'm not trying to say life is over. I'm just saying that the problem is over. We can go back and enjoy our life, have a little drink, you know, think about something that's more important, like what to eat next time. Okay, but let's try to be retrospective here and think about this very important question. Is this a good decision tree? Of course not. Why? Because this thing overfits the problem to the highest degree that you can think of, right? You're splitting this whole data set into classes of one single sample point, just using one feature. And there's no more splitting that can be done, and there's no actually tolerance for any possible error. For example, if this is actually wrong, that you're really supposed to put down 1 plus here, then any new sample point coming in down this row will be classified as an error. So you will have a 100% error rate down this branch. Okay, so this is definitely overfitting our training data. Okay, so now we know the problem, right? That we're overfitting. So let's try to fit. Sorry. We have overfitted the problem. Let's try to avoid that. You've already learned a couple of tricks during class, so I'm gonna leave them out here to remind you. Okay, hopefully this is the still fresh from your memory of a couple of classes ago. All right, we can use post tree growth pruning, meaning that we can remove a node away, but we have only one node here in the tree, so this doesn't work. Okay, we can set the maximum depth, but our tree depth is already the minimum it can be. It's of depth 1, right? So this doesn't work. We can set a lower bound on mutual information so that any mutual information smaller than a particular predefined value will not be considered. But remember, let's try to recall here. How did we find x4 to be the first feature? We find it because the mutual information between y and x4 is actually a maximum. So if you set a lower bound, apparently it won't actually guard against this kind of feature. Yes, we are trying to find features like this with high mutual information between the feature and the target variable, between the attribute and the target variable, right? So this doesn't work. So what do we do now? Let's try to think back to the original problem. Okay, why did we arrive at this really useless decision tree in the first place? Okay, we're following the ID3 algorithm. We're using the mutual information criterion. Both are taught in class, both are well-established methods. They're being widely used, and we didn't do any mistake. We're trying to find the maximum mutual information, and it seems like we're in a deadlock, right? So I guess the only possibility is that the algorithm itself and the criterion itself is just useless. But is this really in that case? No. Okay, and that is the main carry-away message that I hope you guys can learn from this problem. That is, when you're having a problem, carry-away message. When your model fails, think back, okay? We're following this model and the well-established criterion to the most strict degree that we can. But this model apparently doesn't, this algorithm apparently doesn't work on this data set. But since this model itself is actually being widely used, then apparently the problem is not caused by ID3 algorithm. It's definitely going to be caused by the data set itself, right? And in particular, our culprit for this huge problem will be this x4. Okay? Let's look back at the data set. x4 can take on 6 different values. And if you were to calculate its entropy, following the definition of the entropy, this will give you basically 1/6 for every pi log 1/6 summed together with a minus sign in front, and this will actually give you, some just go away, it'll be log, let's use base 2 to simplify the situation. It'll give you log 2 of 6. And we're going to prove later that for any discrete random variables that can take on n different values, the entropy is no greater than log 2 of the number of values. So you can see right away the problem. The problem is not because ID3 algorithm is bad, it's because x4 is a bad feature to start with. And it's bad in the sense that it has the largest possible entropy for any random variable that can take on 6 different values. This is uniformly distributed across these 6 different values, which means that you will have a largest entropy associated with x4, which in human terms means that x4 is completely random. So apparently something completely random will fit to whatever you want it to be. It's like an amoeba. It can take on any shape that you want. But in another sense, in another way, it's also like saying that it's completely useless. It doesn't provide you any additional information, right? So the problem here is that we are starting with a bad feature. And this actually corresponds to the subtitle of this question here, which is like saying that the more data doesn't always mean an easier life. You need to make sure that your data is useful. Okay, not something like a garbage like this. Okay. However, you may say that it's very easy to spot the bad feature in this baby model. We'll just look at the data table, and we'll see that S4 takes on suspiciously way more different values than the other three features, which are basically binary or maybe tertiary. That's it. So of course, you can actually follow your intuition here and think about X4 being the bad feature. And you are probably right. But suppose you're dealing with a real-world data set where you have millions of features, millions of sample point. It's not going to be very easy to just spot right on with your naked eye which bad feature is bad and which is good. So what if we cannot detect it? What if some bad features are very hard to detect, and we're still trying to use the well-established algorithm, the ID3, because we really cannot figure out any other better algorithm than ID3 in a training decision tree? Can we do anything here at all? Since ID3 algorithm is kind of fixed, well, the only thing that we can hope to change would be the criterion, right? So instead of using mutual information, maybe we should use something else. Okay? What should this something else be, or what kind of property should this something else have? Well, let's think back to the nature of this bad feature problem. We call this bad feature because its entropy is very large, right? So we want our criterion to penalize for large entropies. Okay? The larger the entropy is that the feature has, the smaller this criterion should be. Okay? But on the other hand, since mutual information works on so many other cases, we still want to keep its good properties, so we still want to keep the mutual information around. So how do we combine these two information? Well, the most natural choice would be mutual information of target. Excuse me. What's going on? Okay. The most natural choice would be the mutual information of y and your target feature divided by the entropy of the target feature. Sorry. Okay? And this, if you follow Tom Mitchell's book on machine learning, this is called a gain ratio, a shorthand term for information gain ratio. And you can see why we call it a ratio, because these two are both measure of information. This is the information that X explains about Y, and this is the information of the uncertainty intrinsic about X, right? So it's like saying that we prefer X that can explain Y away, but we dislike X that is completely random in itself, right? So by combining that, these two information into this new criterion, we can try to revive the ID3 algorithm. Let's see how it does. Once again, I won't bother you with the details, but if you work out all the numbers you need, the mutual information between Y and the four features, the entropy of the feature itself, and then the entropy of the target variable given the feature, and then eventually you calculate the gain ratio. You can actually work this out yourself. It's really not that hard. But the carrier message is that for x1, 2, 3, 4, For x1, the gain ratio will be 0. Unfortunately, it's still useless. But for x2, this gain ratio will be 0.499. For x3, this gain ratio will be 0.5409. And for x4, our troublemaker, the gain ratio will be 0.3868. Okay, so voila! Just by redefining our criterion for splitting nodes or finding nodes to split, we have averted the problem of dealing with completely random variables or completely bad features. Okay, x3 is definitely usable. x2 is probably also usable. If you go back to the data table, then you can see that x2 actually correlates very nicely with the target variable. It's just not as correlated as x4 does. Okay, so that's the first question. It's, I think, kind of atypical, but it does give you a flavor of what the real-world data set will look like. You should never blindly trust your data. Okay, just because you have, say, 1 terabyte of data doesn't mean that they are all going to be useful or clean as you want them to be. All right, you should always take the size of your data with a pinch of salt and think about, okay, is the data that I collect really useful or not? Okay, so that's first question. And the next one, let's see. Start on a new page. For the second question, I will go a little bit faster, really. For the second question, it's basically the similar problem, a decision tree data table, 4 different features, 1 target variables. So let's try to follow ID3 again using mutual information. Excuse me for being sounding like a broken record, but this is the only algorithm we know about decision tree. Let's see how it fares the problem this time. Okay. You don't have to work out the details just by looking at the data values, then you will probably see right away that x4 prime, and you will see why I call it prime. It's not a typo. Okay, x4 prime and y almost agree with each other. Except at the first data point. Okay, so this will give you the intuition that if you were to calculate the mutual information, once again, this thing will be the max. Okay, so that's why I call it the prime, because this thing once again will show up at the root of our tree. Okay, let's follow the ID3 algorithm again blindly. Okay, because at least this time x4 is not useless. Okay, it's not like the previous question. If you go back to the data table, x4 prime can only take on 2 values, 0 or 1. So its entropy is not that high. It's actually probably the same. I think it's actually even a little bit smaller than the other features, the entropy of x4. This is actually probably true. You can actually check it out. Okay. So apparently our experience from the last question doesn't work here, because the entropy here seems to be innocent enough. Actually, it's probably even more even preferred compared to the other features. And what's more interesting is that if you were to calculate, say, the mutual information between your target variable and any of the first 3 features, 1, 2, or 3, and you are good with math, you will get 0 for mutual information between y and any of them. So there's really no strong reason to not choose x4 just by looking at the data table and looking at all those criteria. Okay, there's no intuitive, suspicion that we have in the previous, like we did in the previous example. So let's just try to build our tree. Okay, x4 will split our data into, let me see, the 0 branch will contain 3 negative examples, and the 1 branch will contain 1 negative example, 4 positive, and we're going to split once more here. I will skip the details, but you will find that x1 will be the next feature to split. It's split on that value, 0 and 1, and at at, give me 1 second to bring up the answer. Okay, and x1, one branch, we will have plus plus, and here we will have minus plus plus, so there's error here. We're going to split again, x2, 0 and 1, here's plus, here's minus plus, and we're going to split for the last time at x3, our last attribute, 0, 1, positive, negative. Okay? Apparently, our decision tree has the accuracy of 100%. And whenever you're dealing with 100% accuracy, you always have to worry about the problem of overfitting on your training data. However, that is not the point of this problem here. So let's forget about the overfitting problem. Let's assume that this is just how good our life is. Okay? But let's go back and try to capture this long journey that we took in building this tree. Okay? Think about this. We have only, what's the size of our data set? Right? The size of our data set is 8. We have 8 data points. What about the depth of our tree? 4. Okay? So it's like saying that the average gain that we have in splitting the node at a deeper level in the decision tree is only a factor of 2, right? What if you have 8 billion sample points? Then do we have to build a depth 4 billion decision tree just to correctly capture this data set? Right? So you can see that even if we don't worry about the problem of overfitting, and even if we have no strong reason to believe that X4 is useless, actually probably the contrary is true, X4 may be quite useful here, we still arrive at a overcomplicated decision tree model. Actually, now I can reveal to you the secret of my trade here. The way I arrive or construct this data table is very simple. For any people who have a CS background, you should know right away, if you forget about X4 feature, then the target variable really is just a simple XOR operation between the first 3 features. Okay? This is our ground truth. This is how I build this table, so it's absolutely correct. There's no overfitting here. However, you can see that by following the ID3 algorithm and the mutual information criteria, we once again miss the target, miss the ground truth completely. We're starting from the wrong place. Okay, so that's what the subtitle for this question is for. Okay, that ID3 is a greedy algorithm, and whenever you're dealing with greedy algorithm, you run the risk of going into a local optimal solution. That may not be globally optimal. And in this baby model here, in this baby question here, you can see that you're missing out on such a simple model. Well, sorry, such a simple ground truth, just by blindly following the greedy algorithm. Okay, so the carry away message is, once again, if your model doesn't work and you have no strong reason to believe that there are some bad features at play, then maybe you're just not using the right feature. They're not bad, they're just not presented in the correct way. Okay, there's no feature in the original table that's called x1, XOR x2, XOR x3. This is missing. In order to find the simple model here, we need to build or engineered this new feature, call it x5. And if you somehow know this thing, or if you somehow spot something suspicious about these three features and came up with this feature, then you will know right away that x4 prime is actually not the first node that you should split on. You should split on x5 and you arrive at the correct answer right away. That's it. Okay? So this actually hopefully will give you some hint or some flavor of the importance of a very important step in any machine learning or deep learning task. That is feature engineering. Okay? Feature engineering is not like that you're using bad features. It's like that they're useful, but not in the way that they're presented to you. You have to figure out some kind of combination, some kind of extraction, or some kind of a dimension reduction. For example, later on in this course when you're learning PCA, it's pretty much like a novel way of doing feature engineering. How do we find more useful features from the features given to us, or from the raw form that the data is presented to us? Okay, so that's the second question. And the third question, so I'm sorry I've been taking a lot of time for you guys, so I'll try to speed up here. The third question will be quite open-ended, so I won't be spending much time on it. This is once again telling you the importance of feature engineering. If you look at the model given to you, it's basically a bunch of negative examples in the center, and then a bunch of positive examples surrounding the negative examples. And the question is asking you, okay, for this kind of classification problem, what kind of model would you choose? Okay, let me bring the screen up to date. Yeah, what kind of model would you choose for this kind of classification problem? Right? Would you choose linear regression? Of course not, because this is apparently not linear. You cannot draw a line anywhere to separate this thing perfectly. The linear regression doesn't work. Decision tree, well, if you split on x and y, maybe you can do something like this. And maybe it'll just split, it'll just perfectly classify these two classes. But apparently you can see that you can classify the negative class perfectly with maybe one or two decision tree, but you have to manually disintegrate the positive classes into all these different subclasses just to make sure that your decision tree works perfectly, right? So it works, but not to the degree that we want. Okay. The k-nearest neighbor will of course also work, but for all those edge points, for example, data point here, if you choose 5 nearest neighbor, you may end up with a situation like this, and you may actually happen to enclose more positive example than negative example, and therefore classifying this point as the wrong label. Okay, so KNN also works to a certain extent, but it will inevitably give you some error. Okay, a single perceptron, if you know what a perceptron decision boundary looks like, it's going to be a line. So a single perceptron, of course, doesn't work because you cannot use a line to separate these two classes. Okay, an ensemble of 1,000 perceptron, well, that probably will work because you can arrange the decision boundary of all those 1,000 perceptrons to be try to follow the contour of the circle that separates your data point, right? So if you have 1,000 of them, maybe they will give you a very clean and separable decision boundary, but you can see that this is definitely overkill, right? Because this is such an innocent problem. You have only two-dimensional data. There's x, there's y, and that's it. And do we really want to use 1,000 models? Remember, one single perceptron is one model, and you have to train it through a whole training algorithm just to learn its own weight. Imagine doing this thing 1,000 times over for this simple problem. It's probably overkill, right? And then deep neural network, whoa, that's even bigger overkill. Okay, so what's the problem here? The problem, once again, is with feature engineering. Our useful information is all contained within this data, but it's presented to us the wrong way. Right now, it's presented to us in this form. given the x and y coordinates, we plot this point out. However, what if we take the polar coordinates transformation? Right? And arrive at a new feature representation. Instead of using xy coordinate, we'll simply use the polar coordinates. And we're going to redefine our origin here. This will be our new origin. So this is where r is equal to 0. All right. And if we use this polar coordinates, then what do the sample looks like? Theta here, r here. Then you will see that when r is smaller than some distance, we have all negative examples. And when r is bigger than some number, a threshold, we have all positive examples. Okay? So you can see that by going from Cartesian coordinate to polar coordinate, we have transformed our data, we have transformed our feature, and we have greatly simplified our classification problem. Because right now, the classification can be done with naked eye. Okay? And if we go back to the model, perceptron can definitely work here. Decision tree will definitely work here. KNN, we also work with much less probability of generating error. And ensemble of, you don't even need to bother with ensemble of perceptron or deep neural network because all those simple models can work. Okay, and later on when you're learning logistic regression, even logistic regression can actually do a very decent job on this kind of data. All right, and it's actually hopeless in the original form. So once again, hopefully I've convinced you guys that a successful machine learning task is really a combination of good model, good data, and good features. They are equally important. We're trying to focus on this component in our class, and unfortunately, we won't be talking much about either of these things in a real-world setting, but you will, hopefully, in fortunate cases, figure out that in real world, it's actually these two things that really matters. Everybody knows about what a good model is. Everybody knows about what deep learning model is, what an RNN is, what a CNN is, but not many people know how to filter out useful information from your data and how to generate really useful informational features. Okay, and there's no golden standard, so the best that I can do here is just to give you a flavor of what you can do. Okay. All right, so that's it. That's the bulk of the meat for the last section, and I will try to speak through the very last question, which is kind of falling back to the conventional side of things. It's about proving some properties and a relationship between entropy and mutual information, so I'll be very quick about that. First, question 4, step question 1, where suppose you have a random variable that can take on n different values, each with a different probability, P1, P2, all the way to Pn, excuse me, with a constraint that they should be probabilities, so they should all sum up to 1 and all of them should be non-negative, then you can actually prove that the entropy of this thing, which is basically negative sum of pi log pi, is going to be bounded from above by log of n. Okay? So this is what we are trying to prove. Ooh, what did I do? Okay. How do we do that? Well, we're going to use something called Lagrange multiplier method. If you're familiar with this, then you should know right away what I'm going to do now. If you're not, I recommend that you search it up on Wikipage, on Google search, or on Google Scholar. Or just go back to your to your friend from math department, and they can explain to you that like in 5 minutes. Okay. So the Lagrange multiplier method is basically reconstruct a target function from this into a Lagrange function that incorporates hx and our constraint in the form of a multiplier. So this is a constant times the constraint that we have. Okay, so that's it. And the reason we want to do this is because now we are going to deal with an unconstrained optimization problem. And our goal is to maximize this function. And of course, if you want to maximize the function, then the obvious way would be to take its partial derivative with respect to all the parameters that you have that this function depends on and set it to 0. Okay, so let's do that for one pi, see what it does. This will be partial h, partial pi, plus this thing taking the partial derivative with respect to pi. This one goes away, and there's only one term that contains pi, which differentiates to 1. So this will give you lambda. And partial h, partial pi, this term, if we go back to this expression, you can see there is only one term like this that contains pi, which is a product of two terms, pi and times log pi. Of course, there's a minus sign. So you can just do the usual differentiation using product rule. That will give you negative log pi, that's one term, and then negative pi times 1 over pi, that's another term, plus lambda. And this, if you carry on the derivation, will give you negative log pi minus 1 plus lambda. Okay, remember this whole thing has to be 0. So this means that we're going to move log pi to this side. This means that let's use base 2, but it can be any base you want. Okay, so this is pretty much like solving equations for using this equation for pi to solve for that. Okay, and we arrive at a sort of a solution for pi. And what's very important about the solution is that you can see on the right hand side, this thing does not depend on the index, on the particular value that the random variable takes, right? We're following the most generic term in the sum. So this holds for all I. This can actually run from 1 to all the way to n. So what does it tell you? What does it tell you? It means that the random variable that maximizes the entropy will have equal probability among all the possible values that it can take. Well, what do we call this kind of distribution, random distribution? A uniform random distribution. Okay? And this symbol is just says, this is actually from statistics, saying that this random variable follows this kind of random probabilistic distribution. And this unif here is a shorthand for uniform. Okay? So it's like saying that a uniform distribution has the maximum entropy. At least among the random variables that take on the same set of values. Okay, which kind of makes sense. If you think about it, entropy is a measure of degree of randomness in the random variable, in X. And the uniform distribution is probably the most random situation that you can encounter, right? Because you have no better, you have no best solution or better solution for any of the values. Every single value is equally probable. So apparently the information it contains should be actually the biggest. The entropy should be the biggest. Okay, So that's the proof. And now let's try to go on and finish the last 4 questions. The last 4 inequalities, really. Given the mutual information as a very huge and ugly expression of probability, I'm not even going to bother write that down. You can actually always go back to your recitation note to look at the details. Then let's figure out what property the mutual information may have, right? First, apparently, mutual information between two variables, random variables, should be symmetric. This is very easy to prove. You just go back to the definition in the recitation note, and then you flip the row of x and y, and you can see that the resulting expression is exactly the same. Okay? This is easy to prove. Second is about the relationship between mutual information and 0. And the answer is that since mutual information is some kind of information, you would expect that it to be non-negative, right? Negative information just doesn't make sense. And to prove this, I won't go into the details. You can come to my office hour if you want all the detailed proof. You're going to need the inequality. You're going to need a Jensen's inequality. The sketch is basically like saying that the pxy log pxpy over pxy. This whole thing is basically bigger than, you can take the log term outside, negative, what am I doing? Yeah, sigma pxy pxpy. This cancels out, and this double sum here, because you're summing over 2 probabilities, they will each sum to 1. So you're basically dealing with a situation where you have log 1 times 1. This will be 0, right? So that completes the proof. This is a very cursive version of the proofs. If you want details, or if you want me to help you work through the details, come to my office hour. Okay. The third relationship is between the entropy and the conditional entropy. And the relationship, once again, is this thing is always no less than this thing. This is very easy to prove. We just show that the mutual information is greater than 0. But the definition of mutual information is just x, y. The definition of mutual information is really just the entropy of the first argument minus the entropy of the first argument conditioned on the second argument. So if this thing is non-negative, so is this thing, and so is this. Okay? And the last one is actually something interesting. Given the entropy of a variable, random variable, and a conditional entropy not on another random variable, but on another random variable taking on a particular value, the answer to this box is actually the question mark, meaning that it could be equal, it could be bigger, it could be less than. There's no definitive relationship between these two quantities, right? And you can see that example. Once again, I won't go into the details, but I can just give you an example right away, hopefully to convince you. Let's suppose that this is the probabilistic mass table for 2 random variables. Each can take on a binary values, 0 and 1. And we have probability like this, 0.25, 0.25, 0.4, and 0.1. And we have that, and you can see that the probability of y taking value of 0 will be the sum of this column, so that's 0.5. and probability of y taking the value of 1 will be also 0.5. Okay, so if we work out the details here, then you can see that the entropy for x itself, you have to basically sum of these, sum of this matrix row-wise. This will be related to the probability of x. Is it related or is it equal? Actually, sorry, this is exactly equal. The sum of these two terms is exactly equal to the probability of x taking 0. Similar to here, the sum here, the 0.35, will be the probability of x being 1. Right? So you're basically calculating a binary variable, the entropy of a binary variable, 0.65, 0.35, and this turns out to be 0.9340. Okay. And if we are conditioning on a particular value of y, say y equals 0, then you can see that in this case, x is equally probable taking on values 0 and 1, right? Because these two are the same. So you're actually dealing with, once again, a uniform distribution. Okay, it's no longer this non-uniform distribution. So this entropy will be, I don't even have to write it down, we just prove that this entropy will actually just be log base 2. You have two possibilities, so log 2, and this will be 1. Okay, so apparently this is bigger than hx. However, if you calculate this, x given y equals 1, which is the second column here, which I will call start, then you can actually work it out. This is going to be, once again, you have to normalize these two terms. So this is basically negative 0.8 log 0.8. By normalize, I mean that you need to rescale them so that they sum up to be 1. Okay, minus 0.2 log 0.2, and this will be 0.8601. So this is actually smaller than the entropy of x. All right. So I just showed two examples and one condition on y equals 0. You have a bigger entropy, and the other you flip the sign between the two quantities. Okay. So going back to the general relationship here, pay very careful attention to these two relationships. Okay. Here you are conditioning x, one random variable, on another random variable completely. Here you're conditioning not on another random variable, but just on a special case that the random variable can take. Okay. Here you have a definitive relationship, and here we don't know anything about that. Okay. So that concludes this section, and sorry for taking so much time of you guys. And hopefully this clears up a lot of confusion, and hopefully this will help you catch up with the thing that you missed during today's recitation. And we'll see you around. Good luck with the homework and the upcoming exam.